So, good morning, everyone. So, this is the last lecture of our first chapter, that is electric charges and field. हम इलेक्ट्रिक चार्जेस और फील्ड चैप्टर डिस्कस कर रहे थे और लास्ट लेक्चर में हमने गॉस लॉ डिस्कस किया था. अब हम गॉस लॉ के एप्लीकेशन देखेंगे. सो लेट अस सी व्हाट आर द एप्लीकेशंस ऑफ गॉस लॉ. Applications of Gauss law. So, as you know that Gauss law is valid for all surfaces, whether it is symmetrical or unsymmetrical, but it is useful for symmetrical surfaces only. So we know that if you have a total flux through a surface, closed surface is E dot delta S, and this will be Q enclosed by epsilon naught. Or if delta S tending to 0, same thing can also be written. If delta S tending to 0, that closed E dot dA, flux through closed surfaces Q enclosed by epsilon. ठीक है? Where Q enclosed is total charge enclosed within the closed surface. Q enclosed क्या है? Total charge enclosed within closed surface. Within closed surface. ठीक है? So we will see application of Gauss law for 4 symmetries. It is useful for symmetrical surfaces. It is useful for symmetrical surfaces. So we will talk about infinite wire, infinite line charge. Field due to infinite line charge. Lambda is uniform line charge. Lambda means lambda is charge per unit length, and that is uniform. Infinite sheet, field due to infinite sheet. Infinite sheet. Infinite sheet of charge having charge per unit area sigma. Sigma is charge per unit area. Third symmetry is spherical symmetry. Spherical symmetry. We will see a spherical shell, or if you have a solid sphere. So we have to see application of Gauss law in these 3 symmetries. Okay? So we will discuss one by one. So let's see first infinite line charge. We have infinitely long straight wire of uniform line charge of uniform line charge, uniform line charge, uniform line charge lambda. ठीक है? So what will be the electric field? So consider a very long wire. Let's say it's a long wire. Or consider a very long wire. It's a very long wire. And lambda is charge per unit length. Here lambda is positive. This lambda is positive value. And this is charge per unit length. Charge per unit length. Lambda is charge per unit length. Lambda is positive, means you have to consider positive charge over it. So, and this wire is infinitely long. Under this assumption only, we can apply the Gauss law, because when it is wire is finite, field at different point will be different. But in this symmetry, it will be a function of r only. Let's say at any point P, if you have to find r distance away, field will same. It is only function of r. So electric field will be function of r only if it is a infinitely long. And what will be direction of the field? Because of this charge is positive. So field will be radially outward. This is the direction of the electric field. If you take some point here, this is the direction of electric field. अगर वायर पॉजिटिव है तो इलेक्ट्रिक फील्ड इज अवे फ्रॉम द पॉजिटिव चार्ज. इफ दिस वायर इज negatively charged, then field will be inward. So direction you know whether it is positive charge or negative charge. ठीक है? So in this symmetry, field will be outward because of the symmetry of the wire. If you draw a circle around this wire, अगर आप एक सर्किल ड्रॉ कर दो तो हर पॉइंट पे इफ यू मूव ऑन द सर्कमफ्रेंस, मैग्नीट्यूड विल बी सेम. ओनली थिंग इज डायरेक्शन विल बी अवे फ्रॉम द वायर, एंड दैट डायरेक्शन इज रेडियली आउटवर्ड डायरेक्शन. उस डायरेक्शन को हम क्या बोलते हैं? रेडियली आउटवर्ड. तो अगर हम एक circle draw करें of radius r, so at each point direction will be radially outward. ठीक है? So if you have to find electric field at any point P on this circle, so you have to draw a Gaussian surface. Let's assume this Gaussian surface is a cylinder of radius r and its length is L. हम एक L length का और r रेडियस का गॉसियन सिलेंडर ड्रॉ करेंगे. इट्स अ क्लोज सरफेस. ये क्लोज सरफेस है. ठीक है? सो लेट्स कॉल इट एज अ गॉसियन सरफेस. गॉसियन सरफेस. और गॉसियन सरफेस क्या है? इट्स अ सिलेंडर ऑफ रेडियस r, लेंथ L. और अगर आप हर पॉइंट पे इलेक्ट्रिक फील्ड देखेंगे, so this will be radially outward. So there are three surface: surface 1, surface 2, and this is surface 3. So what is on surface 1? what will be E dot delta S? क्या होगा ये सरफेस वन पे? E is in this direction and delta S is perpendicular to, ये इस पे n कैप की डायरेक्शन हो गई, तो E और n कैप परपेंडिकुलर है तो ये जीरो होगा। अगर मैं सेकंड सरफेस की बात करूं तो ये n कैप की डायरेक्शन होगी और E और n कैप दे आर परपेंडिकुलर, सो अगेन E डेल्टा S विल बी जीरो। और अगर मैं थर्ड सरफेस की बात करूं, ये n कैप की डायरेक्शन क्या होगी? ये r कैप। So again E and delta S, they are in the same direction. So and what is delta S over the surface of the cylinder? E delta S, they are in the same direction. So this will give you magnitude of E into delta S over this surface will give you 2 pi RL. 2 pi RL. ठीक है? 2 pi RL. So what will be total flux? यहां से आपको टोटल फ्लक्स क्या हो जाएगा? Mod E into 2 pi RL. और what is Q enclosed by epsilon naught? इस गॉसियन सरफेस में कितना चार्ज होगा? इफ इट्स लेंथ इज L, लेमडा इज चार्ज पर यूनिट लेंथ, तो ये हो जाएगा लेमडा इंटू L बाई एप्सिलॉन नॉट। ये L कैंसिल आउट हो जाएगा, तो E को आप लिख सकते हो लेमडा बाई 2 पाई एप्सिलॉन 0 R, और इस डायरेक्शन को हम रेडियली आउटवर्ड डायरेक्शन बोल रहे हैं। R कैप इज रेडियली आउटवर्ड। ठीक है? So you have to remember this formula. What is field due to infinite wire? Lambda by 2 pi epsilon 0 R. R distance away from the wire. Electric field will be same. Only thing is direction is radially outward if lambda is positive. ये lambda positive के लिए है। अगर lambda negative है, so this is minus, I'm writing it as mod lambda 2 pi epsilon 0 R R cap if lambda is negative. अगर lambda negative है तो electric field is towards the wire. So must remember this case. ठीक है? So that is the case of infinite wire. Must remember this formula. If you know values of lambda is given, epsilon naught is known parameter, R is given, you will get the electric field. Chalo. So take an example based on this. Let's see. Let's take an example. Example is an infinite line charge, an infinite line charge produces a field of 9 into 10 to power 4 9 into 10 to power 4 Newton per coulomb at a distance of 2 centimeter. At a distance of 2 centimeter, calculate the linear charge density. Calculate the linear or line charge density. So if you remember the formula, you can directly calculate. It's a matter of calculation only. So because E is lambda by 2 pi epsilon 0 r. So what will be lambda? Lambda is 2 pi epsilon 0 r into E. So you should calculate this value. Since 1 by 4 pi epsilon naught is 9 into 10 to power 9. So what will be, this will give you 2 pi epsilon 0 is, this is 18 into 10 to power 9. So lambda is given by 1 by 18 10 to power 9. R is 2 centimeter. So this will be 0.02 meter. And electric field is 9 into 10 to power 4. So what will be this value? So this will be 0.02, 0.02. This will be 2 into 10 to power 5. So this value is 0.01 by 10 to power 5, or this will be 10 to power minus 7 coulomb per meter. So line charge or linear charge will be 10 to power minus 7 coulomb per meter. So if you remember the result, only then you can find the value. Clear? So note it down. Now next case is infinite sheet. Let's see. Another case is infinite sheet. Uniformly charged infinite plane sheet. Field due to infinite uniformly charged infinite plane sheet. You have uniformly charged infinite plane sheet. Infinite plane sheet. Sigma is charge per unit area. ठीक है? So consider an infinitely long thin sheet. This contains sigma and these charges are positive. It's a positively charged. Sigma is positive. Sigma is charge per unit area. Per unit area. ठीक है? And it's a uniform. So uniform means sigma will be constant. अगर sigma vary नहीं कर रहा है, so it's a constant. So that is uniform distribution. If sigma is varying, so distribution is non-uniform. It's a very thin sheet. So in this symmetry, if you are considering an infinite sheet in xy plane, अगर आप शीट को xy plane में कंसिडर कर रहे हैं, sheet is in xy plane. So in this case, electric field will be, if you see point above, this is the plane z is equal to 0. So I am considering this sheet to be z is equal to 0. So above, electric field will be in this direction. If you see any point below, field will be this direction. Away from the sheet, अगर sheet पे negative charge होगा, so field will be towards the sheet. So from the symmetry, you know the direction of the electric field. So you know at this point, field will be in this direction. Below, this is z is equal to 0. Below क्या होगा? Field is in this direction. So it's an infinite sheet. Field will be perpendicular to the sheet. Now we will consider a Gaussian surface that is a thin box. In this symmetry, consider a Gaussian surface that is a thin box. It's a thin box. And this box extends equally above and below the sheet. ठीक. This is the box. And this box, this point is above the sheet and this point is below the sheet. Let's say this point is 1 and this point is 2. So it's like this. Above the sheet and below the sheet. Point number 1, point number 2. Sheet width is this is the box. And what will be width of the box? Delta. Delta is very small because it's a thin sheet. ये क्या है? एक thin sheet है. तो जो बॉक्स की width होगी शीट के along, that is very thin. Delta tending to 0. तो ये width हम delta ले रहे हैं और ये delta जो है tending to 0. तो ये जो बॉक्स हमने कंसिडर किया है that extends equally above and below the sheet, just like this, equally above and below the sheet, and width is delta. और इसका जो अपर सरफेस एरिया है वो a है. ठीक है? So it's like this as a Gaussian surface. So this upper surface area is a. This width is delta. ये width कितना है? Delta. और ये upper surface area a, lower surface area a. This area is almost 0. This area is almost 0. Delta into whatever be the length. So there are 6 surfaces. 1, 2, 3, 4, 5 and 6. Only 2 surfaces will contribute to flux, upper surface and lower surface. And for all other surface, E dot dA will be 0. ठीक है? So let's see. Consider upper surface. ये surface की direction ये n cap हो गया. Lower surface ये n cap हो गया. और other surface पे क्या होगा? ये 2 direction है. ठीक है? 6 surface E dot dA, but E is for upper surface. Just see E and dA, they are in the same direction, and for lower surface E and dA, they are in the same direction, and for all other surface E and dA is perpendicular, and area of the surface is also 0. E delta into this length into this length. So because this delta tending to 0, so area tending to 0. ठीक है? So what will be total flux? Total flux will be for these 4 surfaces, it will be 0. Contribution of flux for these surface will be 0. Now for upper surface, so E and D, they are in the same direction. ये दोनों same direction में है. Magnitude E is E and area is A. तो upper surface पे क्या हो जाएगा? Mod E into A. And same thing for lower surface. Just check. Lower surface also mod E into A. This is the total flux, and that is given by charge enclosed within the Gaussian surface divided by epsilon naught. So you will get 2 mod E into A sigma A by epsilon naught. ये A कैंसिल आउट हो जाएगा, तो जो इलेक्ट्रिक फील्ड होगा दैट इज सिग्मा बाई 2 epsilon naught n cap. This is the electric field due to infinite sheet. ठीक है? Field due to infinite sheet will be sigma by 2 epsilon naught, and it's a constant value. So if you have an infinite sheet, at each point field will not vary. It is not function of distance. That is for only when you are considering it to be a infinite sheet. When charge is sigma is positive, direction will be away from the sheet. When sigma is negative, it will be towards the sheet. So n cap direction is just perpendicular to the sheet. So I'm taking this direction to be n cap. Here also this direction to be n cap. N cap means perpendicular to the sheet, pointing away from the sheet. So this is the second case. Now, if you have, let's see, we have two sheets, two infinite sheets, and they are placed parallel to each other. Consider, let's take example here. Based on this, now you have one is plus sigma, another is minus sigma. These are two infinite sheets placed parallel to each other. They are placed parallel to each other. What will be electric field in region 1, in region 2, and in region 3? What will be electric field in these different regions? So you have to find field due to individual sheet and then take vector sum. तो पहले हम रीजन 1 में देखते हैं. प्लस सिग्मा के कारण फील्ड क्या होगा? अवे फ्रॉम द शीट. और माइनस सिग्मा के कारण क्या होगा? टुवर्ड्स द शीट. और दोनों का मैग्नीट्यूड कितना होगा? मैग्नीट्यूड इज सेम. मॉड ऑफ प्लस सिग्मा इज सेम एज minus sigma, and that will be, I am taking mod sigma by 2 epsilon naught. So when magnitude is same and direction is opposite, what will be the resultant field? यहां पे resultant field क्या होगा? 0. ठीक है? So in region 1 resultant field will be 0. चलो रीजन 2 प्लस सिग्मा कारण क्या होगा? अवे फ्रॉम द शीट. ठीक है? और माइनस सिग्मा के कारण क्या होगा? टुवर्ड्स द शीट. So what will be resultant field in region 2? In region 2, this will be, magnitude will add up, direction will be same. So this will be sigma by epsilon. And direction is, let's say if this direction is x, so this is x cap direction. Okay? So in between the plates, electric field will be sigma by epsilon naught. Direction will be in the x direction. Away from plus sigma towards minus sigma. Okay? Now region 3. Region 3 में क्या होगा? This will be away from plus sigma towards minus sigma. Magnitude will be same. So resultant will be 0. So in region 1 and 3, electric field will be 0. But in region 2, field will be, they will add up because they are in the same direction. Sigma by 2 epsilon naught, sigma by 2 epsilon naught. So that is sigma by epsilon naught, direction is x cap. Okay? Clear? So that is the case of uniformly charged infinite sheet. Now third symmetry is spherical symmetry. So now we will see thin spherical shell. Field due to thin spherical shell. And it is uniformly charged. Uniformly charged. So uniformly charged means sigma will be constant. Sigma is constant. Okay? So let's consider a thin spherical shell of radius r. Now assume charge q is distributed uniformly over this surface. So what will be sigma? Sigma is given by q by 4 pi r square. Okay? Charge q is uniformly distributed over it. So charge per unit area will be q by 4 pi r square. Now you have to find field outside. Let's say you have to find field outside this cell. R distance away from the center. Now you have to draw a Gaussian surface that is a sphere of radius small r. So this is the Gaussian surface. So Gaussian surface is a sphere. It's a sphere of radius r. It's a sphere of radius small r. So this Gaussian surface, you have a surface is, you are on the surface of a sphere. And if you are considering an elemental area delta S, let's say this is the delta S, its direction will be r cap. Direction of n cap is r cap. And electric field will be also in the same direction, radially outward. At each point, if you draw, if you consider any elemental area, E and delta S, they will be in the same direction. So if you find total flux that is sum over E delta S, this will be given by, this will be magnitude of E, and if you are taking summation of delta S over this sphere, so that will give you 4 pi r square. And what will be total charge enclosed? Total charge will be Q by epsilon naught, because within the Gaussian surface, what is total charge enclosed? Q enclosed is Q. So electric field E is given by 1 by 4 pi epsilon naught Q by r square, and this is radially outward direction. Again, charge is positive, so field will be radially outward. So this is the electric field due to spherical shell outside. So outside, you are assuming that this total charge Q is concentrated at the center O. So if you are considering some point charge Q at the O, then this electric field is just like a field due to point charge Q. So in a spherical shell, this you have to consider all the charges are concentrated at the center, and r distance away, this will be the electric field. Okay? So whenever there is a spherical symmetry, using Gauss law, you can easily find the electric field. Now field outside. This point is, this is the field. This is the field outside. Now we have to see field inside the shell. R less than R. What will be field inside the shell? So that will be given by this radius is R. Charge Q is uniformly distributed. Now at any point P, R distance away, let's draw a Gaussian. This will be the Gaussian surface. This is the Gaussian surface. In a shell means hollow sphere. So inside there is no charge. Charge is distributed over the surface only. So total flux, in same way you will get 4 pi r square. And since there is no charge enclosed, so for inside point, electric field will be 0. Electric field will be 0. Okay? So that is the case of spherical shell. It's a spherical shell. Now we will consider concentric spherical shell. In the spherical symmetry, consider a concentric spherical shell. Thin concentric spherical shell. Thin concentric spherical shell. Thin concentric spherical shell. So let's see this figure. So this inner radius is R1 and this contains charge Q1. Then you have this is R2 and this contains charge Q2. It's a concentric, means both shell have same center. Q1 is distributed over the inner shell and Q2 is distributed over the outer shell. So using Gauss law, you can directly write the electric field. So let's see what will be the electric field in the region when you have 0 to R1, means any point P that lies in this region from 0 to R1. So what will be electric field? Because there is no charge enclosed in this region. Total charge enclosed is 0. So electric field will be 0. Electric field will be 0. Now, if you are considering point that lies in this region, R1 to R2, means one point is here, another point is here, another point is here. So this is region 1, this is region 2, and this is region 3. So this will be region 1, this will be region 2, R1 to R2. So E2 is given by, now if you draw a Gaussian surface, charge enclosed will be Q1. So electric field is given by 1 by 4 pi epsilon naught Q2 by R square R cap. Just see where R is this distance. R is distance from the center. Q1, because charge enclosed will be Q1. Charge enclosed in this region will be Q1. If you draw a Gaussian surface, so you will get mod E2 into 4 pi R square and then Q1 by epsilon. So you can easily write the electric field. Similarly, in region 3, when R is greater than R2, in this region, electric field will be given by 1 by 4 pi epsilon naught. If you draw Gaussian surface in region 3, charge enclosed will be Q1 plus Q2. So this will be given by Q1 plus Q2 by R square R cap. This is the electric field. ठीक है? So in this way, you can find the electric field whenever there is a spherical symmetry. So I have considered the case of thin spherical shell and concentric thin spherical shell. Charge is distributed uniformly. Note it down. Now we will see what are the properties of, so in a spherical symmetry, we have to consider these three, in Gauss law, we have to consider these three symmetries only. That is infinite wire, then you have a infinite sheet and spherical symmetry. Now let's see, till now we have talked about material in which charge is, let's say, charge is distributed throughout the volume. If charge is distributed throughout the volume, that material is called as dielectric or insulator. So we can classify material in two categories. For electricity and magnetism point of view, we will discuss the two types of material. One is dielectrics or insulator, and another is conductors. So you know that these are the solid material, and any solid, there are regular arrangements of atoms. So how this dielectric and conductor is different? In a dielectric materials, electrons are tightly attached with their nucleus. They are not free to move. But in a conductor, each atom will contribute one or more electrons and they are free to move. So that's why both material have different properties. So first I will discuss the properties of conductors, and then we will see in next chapter what will be the properties of dielectric, means how they behave in external field. So let's focus on the conductors. So what are the properties of conductors? Properties of conductors. Properties of conductors. So you have to always see whether it is dielectric material or conductor. So first property is electric field inside conductor is zero. Electric field inside conductor is zero. And I am talking about ideal conductors. I am talking about ideal conductors. Conductor is ideal. Ideal means its conductivity, let's say conductivity, I am representing it by sigma, is infinity. I am considering conductivity is infinite. So you will see when you have a conductor, and if you place this conductor in an external field, let's say this is an external field and it's a conductor. So what will happen? The electron clouds, the electrons that are attached with their nucleus, there are free electrons from the each atom. So electrons will shift towards this side. Why? Because of this external field direction. And nucleus will shift towards this side. As a result, an internal field E naught will develop. This, and what will happen? This field will keeps on increasing as charge accumulation is keeps on increasing. And in equilibrium situation, you will see E is equal to E naught. So inside, as a result, net electric field will be zero. That is the property of conductor, that whenever you place it in some external field, an internal field develops which cancels the external field. So net field is always zero. Inside a conductor, electric field is always zero. Now charge density rho is 0 inside conductor. Because electric field is 0. So according to Gauss law, if you draw any Gaussian surface, even in elemental volume, so charge per unit volume will be 0. Although there is equal number of positive and negative charge, but charge density will be 0. Charge density will be 0. So there is equal plus and minus charge. So charge density will be 0. Charge per unit volume will be always 0. So that's why electric field will be 0. Then any net charge resides on the surface only. Resides on the surface only. Resides on the surface only. If you give any external charge to the conductor, that charge will reside on the surface only, in such a way that electric field inside conductor must remain 0. And fourth one is, on a charged conductor, electric field is perpendicular to the surface. Perpendicular to the surface. If surface charge is positive, it will be outward direction. If surface charge is negative, that will be inward direction. But on the surface, electric field is perpendicular to the surface. So these are the 4 properties. We will also talk about potential in next chapter. You will see potential is also remains constant. But since till now we have talked about only electric field and Gauss law, so I am giving you those properties. So must remember these properties of conductors. Okay? So let's see. Let's take a unsymmetrical shaped conductor. I am consider this to be an unsymmetrically shaped conductor. It's a conductor. Let's say this is a conductor. So if it's a conductor, inside electric field is always 0. Charge density is 0. Any net charge reside on the surface. Let's see if you have given a plus Q charge to this conductor. So this plus Q charge will distribute over the surface only. And this will be distributed unsymmetrically. This is the external charge. And because surface is unsymmetrical, so charge distribution will be unsymmetrical. Now see, and this charge Q will be on the outer surface only. It can't remain inside. Why? Because if there is a charge inside, electric field will never be 0. So that's why this charge will go on the surface in such a way that electric field inside will be 0, because Gauss law is satisfied. Now just see, if I am considering this surface as surface A and this side surface as B. So here charge density at A is greater than charge density at B. Don't confuse with sigma. Sigma I have taken conductivity also, but here I am talking about charge density at A. Just see, on the sharper edge, charge density will be greater. Charge density is what? Charge per unit area. Here sigma, I am talking about charge per unit area. Charge per unit area. Charge per unit area. So now you have to consider surface A, then you have to see the curvature of this area. Let's see what will be area of this curvature. Similarly, you have to see area of this curvature. So this area is large, so charge density will be less. This area is small, so charge density is at A is greater. So that's why charge density at A is greater than charge density at B. So that depends on the curvature of the surface. Smaller the area, larger will be the charge density. Clear? Now see, in this case, because on the surface charge is positive, so field will be what? At any point, field will be perpendicular to it and this will be pointing outward. If charge will be negative, it will be towards it. So electric field will be perpendicular to the surface. When charges are positive, it will away from the surface. Charges are negative, it will be towards the surface. Is it clear? So these are the properties of conductor. Now take another see. Now see, if you have a spherical conductor, what will happen? If you have a spherical conductor, now you have a conductor of radius r and you have given plus q charge. So this charge will be distributed uniformly over the surface. So although E is 0 inside, rho is 0 inside, but surface charge sigma r is given by q by 4 pi r square, because this distribution is now uniform. Distribution is now uniform. Clear? So if surface have symmetry, so charge will be distributed symmetrically. If it is unsymmetrical, so charge distribution is unsymmetrical. Now let us consider a cavity inside the conductor. I am considering a cavity inside. Let's see. It's a conductor and there is a cavity inside. Consider there is a cavity inside. So you know that it's a conductor, so inside electric field is 0, charge density is 0, and it's a cavity. Inside cavity I have placed a charge q. Inside cavity I have placed charge q. So what will happen? Now if you draw some Gaussian surface around this, there will be charge enclosed, so field will be non-zero. So if charge is inside the cavity, what will happen? This will produce electric field in such a way that internal field will be created. And what will happen? Now negative charge will move towards this side and positive charge will develop on this side. And charge accumulation will take place until net electric field is 0. So again, charge accumulation will take place. So in this case, because this charge is positive, So this will be negative, because if this charge is negative, then towards this side positive charge will move and negative charge will move on the outer surface. So because of this positive charge, there will be accumulation of negative charge towards this surface and positive charge on this surface. And this accumulation will take place until the electric field will be 0. So on the outer surface, positive charge will develop, and on the inner surface, negative charge will develop. This total charge will be plus Q, and this will be of minus Q. So plus Q minus Q, total charge enclosed will be 0. Now Gauss law is satisfied here, and electric field will be 0. And on the outer surface, you will get plus Q charge. So from outside, just by seeing this charge, you can guess what should be the charge that is inside. If this charge is plus Q on the outer surface, plus Q will develop. If this charge is minus Q on the outer surface, minus Q will develop. Is it clear? So that is the property of conductor, and this again, just see, charge will be distributed unsymmetrically. Charge will be distributed unsymmetrically. Okay? And if there is some charge outside, so electric field cannot penetrate the conductor. You should remember this point also, that electric field cannot penetrates the conductor. So it means, let's see, if there is some cavity inside, and let's place a charge Q here, and outside, if you are placing some charge Q, so there will be electric field due to this charge plus Q. So this charge Q will be unaffected by this charge Q. So that's why we are saying that electric field cannot penetrate the conductor. So if there is a charge inside the cavity and there is a charge Q outside this conductor, so this charge will not affect the charge Q inside the cavity, because this electric field cannot penetrate the conductor. If charge Q is inside, that will give you the charge plus Q on the outer side, on the outer surface, and there will be charge accumulation inside, so that net electric field is 0. But if you have a charge plus Q outside, this will only, if there is some charge over its surface, this charge distribution will change, but this electric field cannot penetrate, and there will be no charge accumulation inside. So an inside electric field will be always 0. So there will be no force between these two charges. Means this charge Q will not affect the charge Q, or there will be no force between this and this charge. So in that sense, electric field cannot penetrate the conductors. So you should remember these properties of conductors. And in next lecture, we will take some more problems related with conductors and dielectrics also. Clear? So please note it down. Okay, so meet you in next lecture. Chalo, thank you everyone.